Today, machine learning models are fairly mainstream. They are shipping in large consumer-facing projects, also in enterprise projects, and that's what we want to tell you about today. For that, I would like to welcome Nick Spirin from Gigster.
Thank you, Martin. And I also want to thank everyone for coming to this session. This is a repeat of our session on Tuesday. Just really thank you a lot for coming. And a few words about Gigster. Gigster is a consulting company that delivers digital transformation and business impact to enterprises at startup speed. We focus on new technology, AI, machine learning in particular. I lead the AI ML projects. And today we will talk about one particular project that we did for the leading consumer electronics company. And since this is a technical conference, I will show you this slide. We put tiger in a box. Seriously, we built over 20 different models for this client, including image tagging, composition analysis, style analysis, color analysis, and many others. And for this talk, we decided to pick object detection as our model, since it's an exciting model from the research point of view, and also because it opened a lot of different applications for the customers.
And Nick, this is a product that is actually shipping today, a product for professional photographers.
Correct. This is already actually running.
Nice. So tell us more. Why object detection? Why specifically this?
Object detection, as you can see on the slide, by having bounding boxes, we can select images with a specific object and also in a particular location so that it allows for possible overlay of text, for example, for media applications or advertisements. Also, surprisingly for me and the team, we found that photographers do care about images like that, and they call it animal portrait in the same way as we speak about human portraits, and they do differentiate those images from animal pictures at a distance and actively search for such images on the platform that we also built for the customer. And finally, object detection is a type of model that draws bounding boxes around objects, and because of that, it allows object counting and queries like two cute pandas, while image tagging or image classification, which is the common application also in the computer vision space, only supports assignment of binary labels of presence of a particular object on an image.
And for this use case, you have from your customer a data set of over 300,000 images with, I think, something like 600,000 bounding boxes. And what we are going to tell you today is how we took one model, RetinaNet, how we trained it on TPUs to deliver this end-user experience. But I would like to do something a little bit more. Let's train this model here on stage.
Let's do it. And we will truly show the power of TPUs for fast training.
So I will explain in a little bit more depth what I'm doing here, all right? Just in a second, that's what the talk is about. Here I just want to launch the script that will start this training job. So I'm in this one. Sorry, just a second. Here I am. Let's call the model on stage. Okay, and I'm launching it. So it's doing stuff, doing stuff, and I should have a job launched right here. In a second, the job is launched. I'm going to check in my AI platform jobs interface that I have a job running. It has been running for 4 seconds. Let's now dive deeper into what these TPUs are, Tensor Processing Units. So this is a TPU v2. This is a TPU v3. Those are fairly large boards, large like this. You have 4 chips on one board, and each chip is a dual-core TPU. And by the way, on the floor, you have a whole rack of those TPUs. Looks like this. And in Google Cloud, you can provision a TPU either by board, 8 cores, or you can actually get multiple of those boards together in what we call a pod, and they are tied together on a high-performance interconnect that makes them look like, to your application, as just one accelerator. So the only work you have to do is to increase your training batch size to take advantage of all this additional hardware. Nick, between V2 and V3, which one do you like best?
Short answer, V3, and it's not because V3 is the latest version of TPU, but because based on our experiments, combining TPU V3 plus RetinaNet, which we will cover later, it's a model for object detection, TPU V3 was 3.5 times faster compared to TPU V2, and at the same time, TPU V3 is only twice as more expensive. So combining those two things together, the ROI in terms of computation per dollar for TPU V3 for that particular training job is better. So our recommendation, if you do object detection, use RetinaNet, use TPU V3.
Let's have a look at one TPU. What is inside? I told you one board, 4 chips, dual core. What is in each of those cores? So you have a fairly traditional vector processing unit. But the specific part that makes this special for neural network workloads is the matrix multiply unit. It's a dedicated hardware unit that performs 128 by 128 matrix multiplications. And it does so for speed in reduced float-16 precision. So this is a very traditional trick in neural networks to work in reduced precision. Neural network training is fairly resistant to the loss of precision. There are even cases where the loss of precision by introducing noise actually helps the training. Sometimes you even introduce noise on purpose as a way of helping the training. But the traditional, the standard float-16 format, as you can see here, has a different number of exponent bits compared to float-32, which means that it doesn't have the same range. And when you port your model to reduce precision using float-16, you usually get underflows and overflows. So all of these problems are fixable if you know your code, but it's work. And in TPUs, we decided to use a slightly different reduced precision format, which we call bfloat16. And you see it's actually float32 with just the fractional bits cut off. It has exactly the same number of exponent bits, exactly the same range, which means that it's usually a drop-in replacement for your float32s. And there is nothing to be done on your model when you use that. You don't have to do the work of using bfloat16. This is something that is done automatically. You send the data in float32, and it gets downgraded in the MXU on the input, and then the multiplication between two 16-bit floating point numbers becomes again a float32, which is what the result is. And now, how is this unit built, the MXU? So it uses a quite a rare architecture in microprocessors called a systolic array. Try to remember how to perform a matrix multiplication. So a matrix multiply, each point of the result is a dot product of one line of a matrix and one column of the second matrix. And a dot product is a series of multiply accumulate operations. Multiply plus, multiply plus, multiply plus, multiply plus. So the only compute element we have in this whole array are multiply accumulate elements. And I think you will have to spend a little bit more time offline with this animation. But what it does is that you load one of the arrays into, one of your matrices into this array, and you flow the numbers from your second matrix through this array. And if you'll have to believe me, as the data flows through it, and as the multiply accumulates are performed, and the intermediate results get passed to the right, out of this side will come out all the dot products that compose your resulting matrix. The nice part about this architecture is, well, first of all the intermediate results are just flowing on the wire. So nothing to store back to registers or to intermediate memory or anything else. Everything is self-contained in here. And the second thing is that the individual compute element is a tiny, tiny 16-bit by 16-bit multiply and accumulate unit, which means that we can cram lots of them in one chip. And this 128 by 128 array contains 16,000 of those compute units. Of course, it's dual core, so 32,000 in total. Density means power, and power means cost. That's the advantage of TPUs. And of course, you want to know how fast this goes. So some of you might remember my talk from last year when I showed you how to do airplane spotting. I'm using this neural network as a benchmark these days. And so this neural network trains in 4.5 hours on a big, powerful GPU. On ML Engine AI platform now, you can easily get a cluster of those. And with 5 powerful GPUs, I can train this in 1 hour. And I've chosen this example because this is exactly the time it takes to train it on one cloud TPU v2. So just as a rule of thumb, one cloud TPU, 4 chips, roughly equivalent to 5 powerful GPUs. In terms of speed, in terms of cost, it's almost 3 times less expensive because we have a density advantage in the microarchitecture. So now we have powerful hardware. We also need a model, an object detection model. We have a whole library of models, TPU-optimized models, in this GitHub/TensorFlow/TPU repository. Nick, which one did you choose?
We picked RetinaNet, obviously, since it's an object detection model. And we also picked RetinaNet not only because it is the model available in the official TensorFlow repo for object detection, but because it is considered to be one of the best models for object detection in general. And let's talk about it.
You can tell us how it works. Why is it the best?
Yeah. First, before we go deep into the RetinaNet details, I will introduce the overall pipeline that is used for object detection, and then we will cover a special new idea that was introduced in the official RetinaNet paper. So overall, object detection works as a pipeline where we first generate a lot of bounding boxes, and you see them on the slide. Those are also called proposals. And then we do prediction of the class labels and adjustment of the positions of the bounding boxes using the neural net. And there are one-stage neural networks and two-stage neural networks in the sense that in one case, for example, one-shot neural networks such as Overfit, SSD, YOLO, they combine candidate generation, bounding box generation, and detection stages together. They process images only once, and that's why they are fast. At the same time, they are not as accurate. And there are two-stage detectors which separate those two stages into two. They first generate candidate proposals, but then they do sampling and post-processing of the bounding boxes, and then they already predict the class labels and adjust the coordinates. So RetinaNet was designed to address those shortcomings and to be both fast and accurate.
And it's a one-stage detector.
It's a one-stage detector, and it uses the ResNet as a backbone, and it also relies on the pyramid structure of the neural network and the fact that it has inside pooling layers that gradually shrink the size of the image. And it is helpful because when we want to do object detection, we want to be able to recognize objects at different sizes, at different resolutions. And by having the natural structure of the ResNet pyramid, we generate multiple layers of representation, and this is called feature pyramid network, the idea that was also introduced in the paper on feature pyramids. And we use that multi-resolution representation, combination of those feature maps as our image, and then we extend it with two subnetworks. One subnetwork is responsible for classification, and this is basically to assign class label. And the second part is responsible for regression, where we use special type of parameterization which was introduced in faster RCNN paper called anchors. So I'll not go into the details, but the idea here is that we have bounding boxes and we adjust the coordinates of the bounding boxes using the neural net. And that's the architecture that we use, and obviously then we launch the training process.
And so this architecture actually existed before RetinaNet, but you told me it has one problem called class imbalance. What's that?
Let's talk about it a little bit. Object detection. As you can see on the slide, there are only 2 pandas, and those are true positions of the bounding boxes around them in red. And there are a lot of background bounding boxes in blue, and those are negative examples for machine learning. So when you train a neural net, the loss function that you have, if you sum over all potential positions of bounding boxes, the easy cases or the cases coming from the background, they will saturate the loss function so that it will be not sensitive to the true objective that we try to learn from the data set, how to predict the position and class label for real bounding boxes.
And when you say they are easy, you mean that the network makes a small error on them, but small error multiplied by hundreds of background boxes becomes big error, and the pandas get lost in that. And RetinaNet introduced a very clever idea to overcome that called the focal loss.
Yeah, and focal loss, just for you to remember, comes from the word focus, because it actually focuses on hard examples, so examples which are difficult to classify for the neural net. And in terms of like math, it extends the traditional cross-entropy loss by adding the multiplicating factor 1 minus p to the power of gamma. And then the way it works, essentially, if the probability is high, which means that's an easy example, then the multiplicative factor will be very, very small, especially if we exponentiate it. And the contribution of that easy example or the background bounding box will be very, very minimal to the loss function. And if it's the opposite, then it will be capped in the loss function. And because of that, the neural net will be really able to learn the important signal of how to focus on the hard examples.
So that's a clever idea, but this actually works. In this picture, you have various variants of RetinaNet in color, and the letters are various competing architectures. And this is a accuracy versus speed diagram. You see, I put a red line in there for better understanding. RetinaNet is above everything.
Yeah, and as we say in the research community, it's in the upper envelope of the graph.
We have good hardware. We have a great model. What is missing now is a good working environment for data scientists to put this model through its paces. And for that, I would like to show you a new feature in AI platform, which is called notebooks. So AI platform used to be called ML Engine. As we are adding feature, we renamed it AI platform. You're used to jobs and deployed models. The new feature here is notebooks. In notebooks, you can create a new instance that has everything installed in either TensorFlow or PyTorch, and you can select that you want just a standard instance with CPUs, or you can get a GPU with it, or even a TPU. I'll show you how in a second. What you get is an instance and a link, a fast link to open Jupyter directly on your instance. I've done that. That's why it's complaining. So here I am in my familiar Jupyter environment. And actually, in this environment, on this machine is actually TPU powered. Since you have not seen it in the UI, how to create a Jupyter machine with a TPU, let me give you the cheat code. You can do so on the command line. So I have one command line to launch my VM and the second one to create a TPU, and a little bit of glue here to connect the two. It will soon be in the UI. In the meantime, this is how you can get there. So let's do something in this environment. Let's have a look at some data. First of all, I want to show you how to load data. Because TPUs are very fast, which means that it happens very quickly that you get data stored, and you have a limit on how fast you're training simply because the data is not getting there fast enough. So in here, in this notebook, I have a first cell that loads the annotations of this data set. 300,000 images. Those are the annotations, all the boxes. You see it's a wildlife-specific data set. Here are all the categories it can recognize: mouses, hamsters, snow leopards, and so on. And what I like about notebooks is that I can visualize my statistics and eyeball my data set. So for example, I see that I have a couple of fairly large images in this data set. Maybe I will have to pay attention to that. But now I want to see my images. So for that, I'm going to use the tf.data.dataset API. That's an API that is designed to prepare data sets for ingestion by a neural network. I'm starting with here list files. And from a bucket on GCS, I'm getting a data set of file names. Then in this API, you can map any function on your data set. So I'm mapping a decoding function, which is here. It does basically loads the image and calls decode JPEG. And now from my data set of file names, I have a data set of images in memory. I will also need to map and resize my images. And then I have all the tools I need to work on my data set, so I can repeat it across multiple epochs. I can shuffle it. I can batch my data set for training. And a nice one is prefetch. With prefetch, you are telling the system to work on the next batch while you are training on the current batch. So you can do all the pre-processing in parallel with training with prefetch. And in TensorFlow, the way you can iterate on a data set to see what is inside is simply by creating a loop. This works in either TensorFlow 2.0 or if you activate eager mode in TensorFlow. And here I am. Here are my image tensors coming out. So 16 by 16, okay, batches of 16, 384 by 384 images. But you see this is painfully slow. And they're coming like one every second. It's super slow. Why is that? We have 300,000 images, and they are on GCS. GCS can get you great throughput, but GCS, as any storage that is attached through IP, the internet, will have a penalty for every file you access. So getting 300,000 files one by one is not a good idea at all. Won't work. And yeah, I'm visualizing them, so you see what kind of images I have. The solution is to batch your files into bigger files. And for that, we use a file format called TF records. We use it not because it has super special features, but because it can put multiple pieces of data in one file, and it has good support in the dataset library. So let me show you how to use it. Nick and his team, they've done the work of putting those files into TF records. So now I'm reading here from a bucket which has TF record files. And it starts again with list files. I have a list of file names. Then I create from that a TF record data set. Now I have a data set of records. This line is commented out because I do advise you to use this interleave command to apply TF record data set, because with this, you are reading from 16 files at once. And that is how you get a good throughput from GCS. You put your data into a reasonable number of reasonably large files, like 100 megabytes large, and then you read from multiple files at once using the dataset API. After that, I'm mapping a decoding function, which is here. And here, basically, I'm reading from every record all the stuff that Nick has put in there. So there is the image, some metadata, and all my bounding boxes and the classes of those bounding boxes. And that's basically it. So now, again, I can visualize my images, and let me relaunch here a loop that will pull images 16 by 16. So here is my training data set. You see it has pictures and bounding boxes, dolphins, ladybugs, and so on. And this time, as you can see, my batches of 16 images are coming out at a steady clip. This is the speed you want.
And just pause here for a second. This is one design pattern or like programming pattern that we want you to remember, to have a reasonable number of reasonably large files. Reasonable number of files is about 100, 10 to 100, and in size also 10 to 100 megabytes. In this case, you will be able to really maximize the throughput and benefit from tf.data.dataset parallel loading. One additional tip that we want to share is about the bounding boxes and the nuances of the RetinaNet implementation, especially for the data scientists in the room. For managers, it's just like hard, and data scientists should be valued. There was a caveat in the implementation of RetinaNet from the official REPA, where there was a limit on the number of bounding boxes to 100. Somewhere hidden in the code, we thought that it will just work off the bat, and it was silently, stopping, and training was failing. And the practical suggestion for you is to filter out the bounding boxes from the images if it's not very critical for your application. So you have an image, either you skip it or you remove the number of bounding boxes per image so that this pipeline can be used. Obviously, if you really want to build a detector that is capturing a lot of different objects, for example, it could be people tracking for security applications, then you have to work around on that. But a short fix is know at least that there are 100 bounding boxes in the implementation as a hard setting.
I also want to show you how to use a TPU with your own Keras model. So for that, let me use the exact same data set, but I have just taken the first class for every image, and I will build a very simple classifier just to show you how to build a Keras model using a TPU. So same data set, you recognize the data set code here, and the second piece of the code is here a convolutional classifier. In Keras, so it uses the tf.keras.sequential model, and it's a sequence of convolutional layers ending with a certain number of classes, softmax activation, so it's a classifier. Here is what Keras tells me this model is made of. And the 3 lines of code that I would like to show you are here. First, you have one function to find your TPU. Then there is a second function to define a TPU distribution strategy using that TPU. Why distribution? One TPU is 8 cores. 8. So it's distributed training. And a third function that transforms your Keras model into a model that can be trained on TPU. So those three lines allow you to use TPUs in Keras. And if I run them, you will see here in the logs that my 8 TPU cores are showing up. This notebook is actually powered by a TPU v3. And then I can launch the training. Well, there will be nothing interesting here. Normal Keras training will start. It takes just a couple of seconds to start. I think that we can move on because we have other interesting things to tell you. Yeah, here, you see it starting. So, just to recap, this is how you use TPUs in a Keras model. 3 simple lines: find your TPU, define a distribution strategy that uses that TPU, and then Keras to TPU model to get a model that you can train, and when you train it, it will run on TPU. A quick word of what is going on. So this is your VM, your TensorFlow Python code, that's where it's running. You remember that Python and Keras, they represent your neural network as a computation graph in memory. And it's that computation graph that is sent to the TPU. Your TPU never sees your Python code. That's important to bear in mind. The TPUs, they don't execute Python code. They get the computation graph. They use the accelerated linear algebra compiler, XLA, to transform that computation graph into TPU bytecode. And if you are using the dataset API, then your data input pipeline is also a piece of TensorFlow graph, which will be shipped to the GPU. And during training, the GPU will be pulling data directly from GCS. So that's quite efficient. And then finally, this is the code for reading from TF record files. Please don't, if you don't care about ordering of your data, which you never do, you usually shuffle your data, please don't forget to put experimental deterministic equals false, because this tells the dataset API that it can do whatever it wants with the data to get it fast. And then you list your files. You, from a dataset of file names, you get a dataset of records. You map a decoding function to get a dataset of whatever you care about, and then you can shuffle, batch, repeat, prefetch your data. And also, please use the interleave function to apply your TF record dataset transformation, because that's how you can load your data from 16 files at once. So, Nick, how do you like having a powerful TPU v3 at your fingertips in a notebook?
I think having a powerful accelerator is definitely amazing. At the same time, we don't want to pay for powerful machines just to type code, and we also don't want to run around and chase machines that are idle and don't do any useful work, because we have to pay for it.
And how did you solve that problem at Gigster?
Yeah, when we started, we were ahead of the game, and we had to invent some solution from scratch. And we built so-called GDE, which is Gigster Development Environment, and set of processes around it to make sure that our data scientists on the team are productive, and also that we minimize the infrastructure cost. The way it works, we have a few machines allocated to the team for quick interactive experiments, and we also have the Dockerized jobs that we start for training real production workflow models. So we have a lot of Terraform scripts, Ansible scripts that provision the machines, install necessary environment variables, drivers, and so on, and then take a Docker container, run the job out of the Docker container, and save the model to the cloud storage. And that took us a lot of effort to build, and it would be nice if it comes out of the box, or almost out of the box.
Well, yes, Ansible Terraform scripts, that doesn't sound like data science, does it?
Yeah, it's not data science, it's DevOps. We have a great set of DevOps engineers, but yes.
I would like to show you a new API that just came out, where a data scientist can use to launch his notebook as a job without doing a lot of work. It's called Fairing. And that's what I used at the beginning to launch my job, and now let me show you exactly what it is. So, first of all, this is my fairing is the cap of a rocket. Okay, it's where you put the payload. So that's the idea. You have a payload, and you want to launch this payload as a job, so that you don't have to worry about the infrastructure. It will spin up the infrastructure. It will tear it down at the end. What is my payload? So here is my payload. It's a notebook. Looks very much like the previous notebook I showed you. And let's call this one on stage 2. What it does is that, well, it does some exploratory analysis of the data set. Maybe it displays a couple of images. Then I have a training cell. And then when my model has trained, I have an inference cell that does something with the trained model. That's fairly typical of the way I use notebooks to work on models. But now my model is in a fairly good shape. I want to launch its training as a job, and usually you don't want to do this once. You will going to launch it once with this parameter, and a second time with this parameter, and then a fourth and fifth time, and very quickly you have multiple jobs running, which is something you would not be able to do on one Jupyter machine. So this is the Fairing API. It has 3 components. The first one is to know what are the requirements of your job. For that, the easiest is to have a Docker file describing the environment. I was kind of scared of that. It's not my world, but my colleagues showed me that the Docker file was basically these 4 lines listing the pip installs that I needed to do. OK, I can write this. And then the fairing API itself has those 3 calls. So one call, set builder, to specify what is your base environment, the Docker file from which it will be building your job. A second one, set deployer. Here I'm saying GCP. GCP means AI platform, a job on AI platform. And I can specify here what kind of hardware I want. You see, here I'm asking for a TPU v3. TPU v3. And finally, a third line specifying what is the payload. One option is to have a full notebook. Of course, if it is just Python scripts, that works just as well. But if I'm selecting a full notebook, I can specify my notebook file. And if I have any number of sidecar files that I need, for example, here my RetinaNet Python files, I can specify a list of those, and then where I want to put my output. When I run this, what happens is that all these things get packaged automatically into another Docker container, and a job is launched on AI platform jobs using that Docker container. What is it? Here it started. Let me check that in my jobs. Now I have a second job running, launched 4 seconds ago. So I can stop this one. I don't need it. I already launched it at the beginning. And maybe we can check if our model has finished training. So let's see. I should have here, right here, I have this folder on stage, and it has finished training. This numbered folder contains a saved model. So let's see what this model looks like. I need to download this. I'm going to upload it here so that we can see it. Downloads on stage. OK, it's coming up. It will take a minute to upload. See, if I do this, it tells me it hasn't finished. So what I want to show you here is that the result of my job, usually when I launch a job from a notebook, I have to extract some code from my notebook, and then I lose my nice environment, which I'm used to. Here, the result of the job is a fully rendered notebook. So everything I have before training, playing with the data, all the visualizations will be there. My training will be there with all the logs if I want to check something. Anything I do after training, like playing with the trained model, eyeballing that it's actually recognizing my animals, all that will be there as well. So let's see. Now it's opening. And here we go. So if I scroll down, my exploratory data analysis is here. I see my classes. I see my training data with the bounding boxes. I can make sure I didn't screw up my image resizing and throw my bounding boxes off. I have my training cell. I have, of course, all the training logs here. At the end, I can check that this whole training, so full ResNet 50 backed RetinaNet, trained on 300,000 images on a TPU v3, took 28 minutes and 50 seconds to train. And of course, you want to know how good it is, so let's see on a couple of images. Here, I'm showing you evaluation images. So on eval images, in the white outline, you have the ground truth. And you see this fox, pretty good. It did the elephant. I'm not cherry-picking my examples, so you will see false detections here. There is no person, and the chimp is not a bear. The zebra are OK. The polar bear is nice. Here, it got the leopard, the tiger, a little bit of an error on the tiger. The baby pandas are hard. It doesn't have a lot of babies in the data set. So it got 1. I'm actually quite happy about that. In this fairly busy scene, it sees horses and cattle. So that's quite nice as well. What else do I have? I have a jaguar here. Nobody's complaining. Hey, this jaguar is actually a leopard. OK. I didn't know the difference either before I started working with this data set. We can forgive this on-stage built model for not spotting that. It gives me snow leopard there, lion, and so on. So no, actually not bad at all for something that we trained on stage here in less than 30 minutes. This was fairing, a way of taking any payload, but notebook friendly, and launch it as a job. Just a little productivity tool for you data scientists. You say where you want to deploy, you say what hardware architecture you want. This can be a whole cluster. And you say what you want to deploy, and you go.
The expo floor will be closing in 15 minutes. Please make your way to the escalators and main lobby. Thank you.
Thank you, too. So, Nick, we have good hardware, we have good software, we have a nice working environment with notebooks and jobs. It's time to get the work done.
Yeah, it seems that we are short on time, so let's get stuff done. And just a small coincidence here, GSD means also for our company Gigster Solution Delivery Engine, a set of processes that we built to make it happen. And don't mix it with SGD, which is stochastic gradient descent. By having access to TPUs and fairing, we were able to explore a lot of different hyperparameters, train many instances of our neural nets.
And maybe you can tell us where you started from.
Yeah, I will cover it as we go. So as you can see, we show some interesting variations here among all the experiments that we did. First thing to highlight here is that we started from the RetinaNet implementation, not from the TensorFlow official repo optimized for TPU. It was just some other implementation of RetinaNet. And it took us about 3 days to train this model on GPU. I would not say that the order or 2 orders of magnitude speed up is the thing that we want to communicate to you here, thanks to TPUs.
Yes, because that model, you told me, it had some issues. You did a little bit of investigation. You had to train it at a batch size of 2, right?
Yeah, there was a problem with the batch size. There was a problem because of the memory limits, and we only stick with batch sizes of 2. And also, I want to say that when we were delivering to the customer, we had to deliver over 20 different models, and we had like very aggressive timeline. So we shipped it to production and decided that we will get back to it during the second iteration of the product. And after that, we partnered with Google to start using TPUs for the process.
So on TPU.
So the thing that we want to highlight here, it took us about $200 and 3 days to train a model of comparable quality that we were able to get with TPUs for $7. So that's a great value. And obviously, RetinaNet optimized for TPU is a great contribution to that number. The second thing that we want to highlight is the best model that we got. It is the highest ever accuracy in MIP, one of the metrics that is used for evaluation of the quality of the object detector. We used our favorite TPU v3, image size 512, and we trained it for 10 epochs, while in the past we, I think, did 3 or 5 epochs only. Just because of the time limitations, we didn't have the luxury to train our neural nets and wait until all the experiments finish, until we find great combination of hyperparameters. And here you see that with TPUs, we were able to train it in 2 hours to get this quality. So that's a win. And we are super excited to show you this model here on stage as well. This is the model that's currently integrated into the product, and it's serving real customers.
So let's see. This one, here in my notebook, I have a little utility. Oops, please go up, where I can, so let me restart this from the beginning. And instead of training, I will just say, please reload from a trained model. It's a 512 pixel model. And I will simply skip the training part and go directly to inference. Here we go. So now the model is It will get there in the, it's reloading from a saved model. And then again, I will be getting random images, not cherry picking anything, random images from my eval data set. Now it's computing the boxes on those images. And you see the chimp is perfect, the polar bear is perfect. You still have in white the ground truth on this eval data set. What else do we have? That's probably not a ray, it looks like a shark. We have a gorilla here. The wolf, I'm not sure, but the Komodo dragon is perfect. Let's see on these more challenging images. Leopard and jaguar, and this time in this busy cowboy scene, it actually sees the little dog here. And my favorite, it got both pandas right.
Design customer-centric metrics. Make sure that 2 pandas are detectable.
So this was the model. And I think what we wanted to highlight is that speed, velocity of your data science team is not just for their comfort, it's for the cost of what you pay, but also you can experiment more and get better results. And you actually did even more experimentation.
Yeah, more experimentation. It's how to use TPUs for inference. And by default, we already know that TPUs are very powerful machines, and they expect big batches. While when we serve models in production, the typical workflow or load pattern is to have 1 image at a time, hits API endpoint, we do the processing, and so on. And if we use TPUs in that scenario, probably that will not fully utilize the power of TPU. We thought about some other workflow that will benefit from TPUs. And actually, we found this workflow in the project. It's not the theoretical workflow or just workflow for this presentation. In our case, we had a data set of over 100 million images, and we had to build a visual search solution on top of that data set. So what we did, we had a pre-trained neural net. We passed all images through this neural net to generate embeddings. Then we indexed that data set of vectors using the face package, and then we got the nearest neighbor approximate search built in. The entire stack supports visual search. And for that purpose, we again use TPU v3. And as you can see on the slide, it is the fastest and the cheapest alternative to make sure that we can complete this very complex, massive indexing job that combines the generation of embeddings and supporting the visual search.
Thank you, Nick. So we talked here about building neural networks, optimizing them. But there is actually a lot more in a full-blown project than that. This is kind of the workflow you're using. It's very complicated.
This is the workflow that we use to develop for the enterprise. And it's very different from having a Jupyter notebook on a laptop or even connected to the cloud machine. We have the environment where our data scientists do training and experimentation. Then we upgrade it to the environment where we demo our models to the customer every 2 weeks, just following the agile iterations. And we have some representation of the customer. I will not start pointing. Then we upgrade our models into the environment where we do the first integration of machine learning with the web mobile part of the product. This is where we do the testing at the program level, and then we start already moving to the client environment where we have app staging and app production.
And so what I see here is that you need to move all those workloads between yourselves and also between you and the client.
Yeah, it's very critical for Gigster because we first build it using our talent network, and then we have to hand over code to the client and also make sure that they can maintain that code base, contribute to that code base moving forward.
I think you have a perfect use case for Kubeflow.
Yeah, we are currently looking into Kubeflow. We are not using it right now, but this is one thing that could help us and you standardize the development of the pipelines and make it shareable within your organization and also with the client organization.
Shareable and reproducible. So just a shout out to Kubeflow. If you are facing these problems, that is something you can also look up.